Okay, so hi guys. So in this video, what I want to do is I want to go over the idea of continuity and discontinuity in Calculus 1. I don't think I've ever made a video on both of these topics in calculus at all. So I'm gonna kind of just I don't know how long this video is gonna be, to be honest, but I am going to kind of just define what these things are. What do we mean when a function is continuous? What is discontinuity? You know, what are some types of discontinuities? When do they happen? All that good stuff. So I mostly want to do some some mostly definition of this kind of stuff, and then I guess in another video I'll do more separate examples, or I can do all of them in one if I have time, but um, I just don't want to make the video too long. But anyways, so I'm sure in pre-calculus we've kind of touched a little bit on continuities, so um, obviously, we always and mostly algebra has a lot to do with this. So I'm gonna state the actual calculus definition. So in and by the way, the book that I'm using is again Calculus Early Transcendentals. Can't write today. Transcendentals. And then I believe it is the 8th edition. So 8th edition. And it's by James Stewart. So the way that I'm gonna define this this topic, continuity, and I'm gonna use the actual definition that I have here. So a function, and let's call some kind of function f, right? So let me kind of just go in here and is continuous. Let me write this down, guys. 1 second. Okay, guys. So this is the definition of continuity, basically. So this is kind of the limit definition of it. And yes, it does involve limits. But so usually this is different from the idea of a limit. I don't want to say that, um, you know, that I don't want anybody like it. They do have, you know, they do go hand in hand, and they do have some relationship. But uh, what I'm trying to say here is that continuity and limits, of course, limits play onto continuity, but I don't want anybody to think that every limit that you take is equal to this, because sometimes that's not true. Um, so, uh, basically, this is the definition of continuity. A function f is continuous at a number a if the limit as x approaches a of f of x is equal to f of a. So basically, um, you know, and also and also there are there are three rules for this. Obviously, there are three rules for this to be true. For this, in order for this to be true, right? Um, so basically number one says that f of a f of a is defined um so let's just do it this way. Hold on. So f so number one, let me kind of just write this down. F of a, this is f of a, is defined, and this just means that um, a is in the domain of f. You know, this is just kind of the algebra definition of that. So that's basically, you know, of f, right? So that's just, it's pretty easy. That first rule is pretty easy to understand. Basically, we need f of a to be defined. The second rule is the limit as x approaches a. So second rule is the limit as x approaches a of f of x has to exist. So this has to be true in order for this to be continuous, for the function to be continuous. And then number three, or to be for it to be continuous at x equals a, excuse me. And then number three is that the limit as x approaches some number a of f of x has to equal f of a. So this has to be true as well for a function to be continuous at a specific point, right? So that is the third rule. Now um, now of course, like I said, and also I want to kind of touch base on the graphical definition. Um, Sorry about my handwriting, guys. I'm like, it's very squiggly. So the graphical definition, and the graphical definition is that in order for, so like for example, if a curve can be continuous if there is not a specific hole or a specific break in the graph. So my pen kind of has to keep going here in order for the function to be continuous. It has to keep going. There can't be any restrictions or any like, you know, um any kind of like, you know, holes or discontinuities. That is basically, if it's not continuous, then there's a discontinuity at a certain point or all over the place. um and actually, I don't think there would be one all over the place, but at a specific point, and we'll touch base on that in a minute. So um so if it is not continuous, if f of x, so if f of x is not continuous at x equals some value a, then f of x is discontinuous, or basically, you know, then there is a discontinuity, then there is a discontinuity at x equals a, right? So, and so what I want to say is that if this is true, I don't want to confuse the definition up here, but if it is not continuous at x equals a, meaning like if there's like a break or something, then either the limit as x approaches a does not exist, f of a is not defined, or the limit as x approaches a of f of x does not equal f of a. It's basically the opposite of these three things. So if it is discontinuous, if it is not continuous at x equals a, then these three things, one or two or all these three things are not true. Um, so that has to be true in order for this has to happen in order for it to be not continuous. Um, I will explain more on that in a minute. Um, so what I, of course, you know, this is the most basic definition. If f is not continuous at x equals a, then there's a discontinuity. That's kind of the basic idea of discontinuity, right? But when it comes to graphically, um, we want to go more, you know, we want to touch more on, well, go more in depth with what does this all mean? How do we see this in terms of math problems, right? Instead of just definition. Um, so one of the things is, and um, for example, um, if I have a, so I wanna just kind of go over some examples, right? This is, let's say we have some kind of curve, but let's just say hypothetically that there is some type of hole in this curve here. There's some type of like hole, or this gap um in this curve, like this curve. And I know that that looks like a really, let me just kind of do this. Hold on. Let me kind of fix it here. So like that. Let's say there's something like that. And let's say that this point, we want to call it A, and this curve here, let's just kind of hypothetically do that. And I'm gonna actually, hold on guys, let me do it this way. I think that'll be better. And then let's say that this is kind of the, the this right here is f of a right here. So f of a. And let's say that this whole curve, this entire curve is really what the function f of x is. Let's just call that f of x because it's just a function. It's a curve. It's a function on a graph. And so when we see something like this, basically we know that if I run my pen through this, so let's just say I'm drawing my pen going through this curve, and what I want to happen is that I want to make sure that there is no type of gap, but then there is, because this right here is, there's a hole right here. So this tells me that because f of a is undefined, then f of x has a discontinuity at x equals a. So that's just a very basic example, guys. That's one type of example. Um, of course, you know, we also want to say, for example, let's just kind of um, go over another type of example, right? And let's just say that there's a curve. So let's say, for example, I'm gonna say that there is some kind of curve, and and right here, so that let's say there's like a discontinuity or a hole right here, right? So let me just kind of draw that really quick. 1 second, guys. 1 second. Okay, so let's say we have something like this, right? And we know that right here, for example, that um, let's just say, and this function, by the way, I'm gonna just say what this function is. This is f of x equals x squared minus x minus 2 over x minus 2. Hold on 1 second, guys. So, so basically what's going on here is that there's some kind of, and of course I don't know for sure if it's equal to 2, but this is a rough sketch. Basically this kind of discontinuity happens, and what we call this actually, guys, is a removable, I think it's a removable discontinuity, if I'm correct, right? Because removable discontinuity. So this kind of discontinuity. This kind of discontinuity happens when there's a restriction. Usually, algebraically, for example, here, this is usually this function here, f of x, has a discontinuity, an infinite, or I'm sorry, removable discontinuity at x equals 2, because of the following reasons. And what happens is, so basically if I do the limit, as x approaches 2 of f of x, of the function x squared minus x minus 2 over x minus 2, then I want to know, is this equal to f of 2? Right? Because I want to see if this is true. We need to know if this is true in order for this function to be continuous. And if you guys forgot the definition, you can go back in the video and kind of see what I talked about. We want to make sure we understand the rules, right? So this is one of the rules, that this has to be true in order for this to be continuous. So I can show y'all why this is not true. So basically, obviously, if we do the limit as x approaches 2 of x squared minus x minus 2 over x minus 2, we know that we're going to get 0 over 0, which means, oh no. So we have to understand how to do limits, right, guys? So here, what's going on is that, you know, obviously this does not equal f of 2, because like I said, let me just kind of plug this in 1 second. So if we evaluate the if we evaluate the point on this graph, or on this expression here, we're going to say f2, and we're going to do the quantity 2 squared minus the quantity 2 minus 2 over, and then it's going to be 2 minus 2. So as you can see, this becomes 4 minus 2 minus 2 over 0, which is 2 minus 2, because this becomes a 2, and then over 0, which means 0 over 0, which means, oh no, right? So obviously, in order to find this limit, we need to do some other things, right? And like I said, if we find the limit, we know that x squared minus x minus 2 is really just the quantity x minus 2 times x plus 1 over x minus 2. And it, like I said, if we put it over x minus 2, right, this is what it becomes. Now, we know that these two cancel out, so these two cancel out, and we know that this is just equal to x plus 1, but this is true such that x does not equal 2. So, so basically, wherever there's a vertical asymptote and where it really does cancel out, then there is a removable discontinuity at that vertical asymptote or at that denominator, whatever denominator cancels out. So that's the idea of removable discontinuity. And because we know that the limit, so if we find the limit as x approaches 2 of this, we know that it's going to be just going to be 2 plus 1 by direct substitution, which is 3. But again, this does not imply, so what I want to make very clear is that although that's true, although the limit does exist, it still doesn't equal f of 2. F of 2 is undefined. So because in the original function, when we plug in x equals 2 for this, it's undefined. It's 0 over 0. So obviously, we know that this function is not continuous, and like I said, because it cancels out on the bottom, or the denominator cancels out, and there's a restriction at that denominator, then this means it's a removable discontinuity. I really hope that makes sense, guys. I'm really trying. So, let's see here. So then that's one type of discontinuity. Another type of discontinuity, let's see here. So, so that is one type of discontinuity. Now, what would happen if I said, well, it's not defined here, but it's defined over here, right? It would still be a removable discontinuity. Although f of x exists, so let's kind of do a little bit of another kind of sketch here, and I just want to do like like this, and I want to say that there's a kind of a hole there, and let me kind of just erase this. So give me 1 second, guys. I'm just gonna do this off camera. Okay, so what I want to go over in this example specifically, because this is a little bit different than the previous one, is that so obviously looking at this line here, we know that at x equals 3 there's a hole at x equals 3, right? And really this point is undefined. We don't know what this one is, but we know that this point right here is really defined by 3 comma 2. So you have to be careful, again, with the rules of continuity, specifically removable discontinuity, or in general, continuity in general. So one thing is that we know that f of x is defined at x equals 3, because we know that that's true, because obviously it's 3 comma 2. F of 3 equals 2, so we know that that's true. But so we know that that's true, but sorry guys, my throat is like, I don't know why I keep doing that. Basically, we know that f is defined at x equals 3, because it's f of 3 equals 2. But what about the limit as x approaches 3 of f of x? Right? This curve I want to call f of x, actually, this line. So this is f of x, right? And we know that, I'm just color coding here so that you guys can understand what I'm putting. So obviously the limit as x approaches 3 of this, to find my limit, I'm gonna draw my line. And you see from the left and right endpoints that I'm approaching 1. So the limit as x approaches 3 of f of x is equal to 1. But again, does the limit as x approaches 3 of f of x equal f of 3? So does the limit as x approaches 3 of f of x equal f of 3? Obviously, the limit as x approaches 3 of f of x is 1, so we know that this part is 1. And then, like we said earlier, f of 3 on part 1 here, we said f of 3 was equal to 2. So obviously, we know that 1 does not equal 2. So because that's the case here, we know that f of x has a removable discontinuity. So anytime you see like a point that is defined and some kind of like, some kind of line that goes through some other point, but it's undefined at this other point. So basically, if you see a line like this or a curve like this that goes through this kind of point here, but then there's another point that's defined at that same x value, it's a removable discontinuity. Okay, guys, I'm probably over explaining it, and I do apologize, but I really want to make sure this is very clear. Now, another type of discontinuity that I want to touch base on is a jump discontinuity. Now, of course, these are more, we did kind of look at these a little bit when we did limits. And what I mean by that is we looked at a kind of a picture of how that looks. So a jump discontinuity can happen at, it can happen actually at piecewise functions, but usually it's more with curves that are like, it usually, when we're given a jump discontinuity, it's kind of like you're given a curve, but then, and let's say there's a hole here, but then there's another curve that kind of goes in this same x value here. Let's say here's a, right? And then there's another curve that goes kind of right here, and it just kind of spirals off to somewhere else, right? This is what we call a jump discontinuity, because what happens when let's say here, for example, let's just kind of do with a highlighter. What happens as I highlight my curve here, I'm going to A, I'm going to A, I'm going to A, but then I'm jumping. You're gonna jump to this. So then I'm gonna jump to that, and then it's gonna keep going, keep going, keep going. So that's why this is called a jump discontinuity. And usually, I'm not exactly sure, you know, for example, if we look at a piecewise function, I feel like this does happen with mostly piecewise functions. Um, but let me kind of think of an example. So if I have f of x equals, let's do x plus 1 such that, I don't know, let's do x plus 1 such that x is greater than 1. And then I'm going to do, I don't know, let me do negative x, actually x plus 1 such that x is greater than 1, and let me do negative x such that x is less than 1. Less than or equal to 1, let's do that. What would happen is, and I'm going to just draw a rough sketch here, is basically, if I look at this one here, so this is kind of the example of jump discontinuity. So what happens here is that for example, for x plus 1 such that x is greater than 1, say 1 is here, 1 is here, and I'm gonna go, so let's say it's undefined at x equals 1 because it's greater than 1, right? So we have to understand how to graph piecewise functions in order to do this. So let's say that this is kind of what happens here, but only such that x is greater than 1. And we know that this is, this is it right here. But let's say we have another type of of graph such that let's say I don't know, hold on, let me do negative x. I'm gonna do negative x minus 1 maybe such that x is less than or equal to 1. So if I do that, it's gonna kind of go, let me do, actually, 1 second, guys. Let me kind of sketch this. All right, so I decided to go with this example. So let's say that, for example, we have this piecewise function, and we know that obviously, the limit, and what I want to emphasize here is that yes, this is a piecewise function, but there is obviously a jump discontinuity here. When I so like, let's say I'm gonna do it with this pen here, with my pen. I'm gonna see here what happens as I get, closer and closer to this. I'm gonna jump over here and I'm gonna keep going. So this is considered a jump discontinuity. Right, guys? Because it jumps. It really jumps. So we have to kind of graphically see how it looks sometimes in order to see, well, is it a jump discontinuity or a removable discontinuity? Now, I will say this. If they give you one where f of x, so if, for example, we have some piecewise function where f of x is equal to like x minus 1 such that x does not equal 1, or let's say, I don't know, let's say x is greater than 1, and then they decide to say, well, I don't know, hold on. They decide to say, they decide to say, that it's x squared plus, let me do, x squared minus 1 such that x is less than 1. And what would happen is, in the graph, so obviously if we have x minus 1 such that x is greater than 1, it kind of looks like this. But again, there's actually, right here, there's a hole at x equals 1, right? So this is the first sketch of that. And this is x minus 1, right? So like this, and then obviously it's such that x is greater than 1. But then let's say they give you another one and they say, well, let's say they say, I don't know, x squared minus 1, and they say, well, that's only true such that x is less than 1. So this is such that x is greater than 1. But if I look at this right here, x squared minus 1, such that x is less than 1, what this is going to look like is it's going to go right here, but it's going to go, actually, let me fix that. 1 second, guys. It's going to look like this. So it's going to look like this, something like that, right? It's a parabola, but so basically we know that, I mean, obviously, and let's do, let me actually, this is less than or equal to 1. So, but obviously we know for a fact that this is still considered a discontinuity because it's not defined. It's the limit as x approaches, and actually, I'm not 100% sure on this, to be honest, but I'm pretty sure this is a discontinuity. If I'm wrong about that, guys, please do correct me. But this is kind of the idea of, you know, of jump discontinuity and removable discontinuity. Now there's one last one that I want to go over. Somebody please let me know if this is true. I'm not 100% sure. I do think that maybe there's a discontinuity here. But then again, I am not sure. I'm not 100% sure. I think it's removable discontinuity, but I'm not 100% sure. So then one last thing that I want to go over in this video, guys, is the idea of infinite discontinuity. So infinite discontinuity mostly happens where the limit as x approaches a of f of x from the right does not equal the limit as x approaches a from the left of f of x. But what I want to emphasize is that this is only true such that there is a vertical asymptote at x equals a. So what I mean by this, for example, this is an example. If I look at, I don't know, let me kind of look at this, for example. So let me say, I don't know, f of x is equal to 1 over x squared. And if I look at that on its own, right, we know obviously that there is going to be an asymptote or vertical asymptote at x equals 0. Now, now, the way that this looks, the way that this function looks, and I'm gonna sketch it for you guys, is it looks kind of like this, kind of like a mountain, kind of like a, I don't know how to call this, like a, I don't really know how to call that. I always call it a mountain or like a volcano, kind of volcano shape kind of thing. So basically, this is the function of f of x. Now, obviously, we have a vertical asymptote at x equals 0, because if you remember from algebra that to find the vertical asymptote of this function here, we say 1 over x squared, and we know that I'm going to make this equal to 0, so x squared equals 0, and then to solve for x, right, I'll just take the square root of both sides. I'm going to get x equals 0. And this is my vertical asymptote. Now, now, obviously, you know, if I look at this, I know that from the left-hand side, I'm approaching, you know, as x approaches 0, from the left, it does approach 0. It does approach infinity from the right as well. But remember that in order for it to be an infinite, or in order for it to be in terms of discontinuity, basically, and actually, this is sometimes true, this is sometimes not true, okay? I want to emphasize that. I'm sorry, guys. Oh my god. So, in this example, obviously the limit as x approaches 0 is infinity. From the left and right, it is infinity. But in terms of, you know, in terms of there being, basically, you know, and actually, let me, 1 second, guys, 1 second. Okay, let me kind of redefine this idea, guys. An infinite discontinuity happens where, so basically, an infinite discontinuity can happen where there's a vertical asymptote at x equals some number a. I don't want to say that the limit as x approaches a from the left does not equal the limit as x approaches a from the right, because that's not going to always be true when it comes to continuity. Let me repeat that. When there is a limit, so basically what I'm trying to say here is that the limit as x approaches a from the left, so like here, as x approaches 0 from the left, is going to be infinity, and the limit as x approaches 0 from the right will also be infinity. But that does not tell me that, you know, because obviously the limit as x approaches a, or as x approaches 0, of f of x is really infinity. But at the same time, that does not, how do I say it? That does not tell me, you know, what I'm trying to say here is that we have to look at this idea here in order for there to be an infinite discontinuity. Do not pay attention to, like, in terms of the limit from the left and right hand side, because I feel like if we look too much at that when it comes to infinite discontinuity, it's going to be very confusing. And I don't want to confuse you guys more than, you know, if y'all are already confused. But my point here is that wherever there's a vertical asymptote at x equals a, like something like this here, where you see a kind of a dashed line here, we know that at x equals 0, so basically for f of x equals 1 over x squared, there is an infinite discontinuity at x equals 0. So I'm going to recap, guys, because I feel like this video had a lot of information. Number 1, we talked about what it means for a function to be continuous. Obviously, a function is continuous, you know, if I can run my pen, you know, if I can run my pen through the curve without there being any kind of restriction. That was the first thing that we discussed. So f is continuous where there are no holes or breaks on the graph. Number two, we also discussed the three conditions to be met, right? So in order for it to be continuous, the limit as x approaches a of f of x has to equal f of a, and then f of a must exist. So that was number two, number one, number two, number three. And number three is that the limit as x approaches a of f of x must exist as well. That was another thing that we discussed. And then the other parts that we discussed as well were the algebraic kind of rules for continuity, right? So for example, and also what it means, what discontinuity means, right? If there's a hole or break on the graph, we obviously know that if we have a curve here, there's a hole right here, and let's say this is a, this is at x equals a, then we know that this function has a discontinuity. At x equals a. And then another thing that we discussed was the idea of specific discontinuities. So there was the idea of removable discontinuity. So, and this is algebraically, right? Discontinuity, and we know that if we have x minus b times x minus a over x minus a, then f of x, so if, let me just write this down really quick. And sorry guys, I'm trying to do this really fast because I know this video is already very long. If f of x equals x minus b times x minus a all over x minus a, then f of x, it has a removable discontinuity at x equals a. That is the idea of removable. And another thing is, we talked about jump discontinuity. So jump discontinuity, the key word for this is jump. So this happens whenever we have a curve, but then there's like this other curve here, and we can see here that it's like it jumps. There's a jump or a gap here, right? That's called a jump discontinuity. So graphically we can see that that's very common. Another thing is, let's see here. And then the last thing that I talked about was the idea of infinite discontinuity. So like I said, infinite discontinuity happens wherever, whenever we have some kind of curve, and where happens, like I said, happens where there is a vertical asymptote at x equals a, some number a. Okay guys, so that is all, like, these are all the ideas of what continuity is, what it means, for what jump, infinite, and removable discontinuity means. If this video ended up being so long, I really do apologize. I really wanted to go over continuity and discontinuity definitions and all this good stuff. Just some quick examples. I will probably make more videos on individual examples, but that is like the whole idea of what it means, what continuity means, what the three types of discontinuities are, um, and the restrictions, all that good stuff. So I really hope this helps, guys. And with that being said, thank you so much for watching. And also, please like, comment, and or subscribe. And also click the notification bell to receive notifications from this channel. And with that being said, guys, thank you so much for watching. And I will see y'all in the next video. Bye, guys.